This is Mr. Beck Does Your Homework, question number 2. Consider a wheel of radius 1.48 meters, and it's going to be a solid disc, by the way, mass 9.1 kilograms, and moment of inertia 1/2 mr squared, which is good because that is what a solid disc has for a moment of inertia. The wheel rolls without slipping in a straight line in an uphill direction 19 degrees above the horizontal. Okay, let's stop and draw a picture here. We have a hill of some sort. We've got a wheel, and that wheel is rolling. It turns out that this angle for me is 19 degrees. Okay, so I've got a wheel rolling and going on up the hill. So let's see. The wheel starts at an angular speed 16.3514 radians per second. That's going to be my angular velocity. So that's my initial velocity, omega. But the rotation slows down as the wheel rolls uphill, obviously, and eventually the wheel comes to a stop and rolls back downhill. So the wheel's going to go up slower, 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 reach a highest point, and then turn around and come on back down. How far does the wheel roll in the uphill direction before it stops? This is asking for this distance here to here that it rolls uphill before it stops. So I'm going to call that x, some distance x that it rolls uphill. Now, if we look at this problem, we are going to see it as a conservation of energy problem. So I have it moving at a certain velocity, and it's going to have some energy when it's in this state. It's going to have some energy when it's in this state, and the energy is going to remain the same as it rolls uphill. So at one point here, while it's rolling uphill, I have some kinetic energy because it's moving. I have some rotational kinetic energy because it's spinning. And that's it there. When I get to the top of the hill, the type of energy I have is going to be gravitational potential energy. And since I know energy is conserved, this total is going to equal this total. So my kinetic energy is 1/2 mv squared. My rotational kinetic energy that I'm going to add is 1/2 I omega squared. And that is going to equal my gravitational potential energy, mgh. Stop for 1 second. That h will give me the height here, h. If I'm going to figure out the distance that it travels, which is my x here, I have to figure out, if I know h, then I'm going to have to work backwards with this angle to get the x using some trigonometry. But that should be easy enough. So we'll worry about that when we get there. So 1/2 mv squared plus 1/2 I omega squared equals mgh. I here is going to be my moment of inertia, 1/2 mr squared. So I'm going to rewrite some of that. Oh, and before I do, my velocity here, I don't know. They don't give me the original velocity. What they do give me is the angular speed. So I'm going to have to calculate the actual velocity from the angular speed. But I know that omega times r equals my velocity. So if I take my given omega and I multiply it by my radius, which they give me here, then I'm going to get my translational velocity. So I can actually write that. So I'm going to have 1/2 of m times omega r parentheses squared plus 1/2 of, now what was I? I is 1/2 mr squared. So that's going to be another 1/2 mr squared times omega squared equals mgh. If you're paying attention, you'll see that the mass cancels out in all of this. So I've got a mass here, I've got a mass here, I've got a mass here. So I've got 1/2 of omega r squared plus 1/2 of a half will be 1/4 of r squared omega is going to equal gh. And with all of this, you can easily solve for h. Now, once you have h, in order to get x, then you're going to have to realize that x times the sine of theta is going to give you your height. So if you want x from your height, then x is going to be your height divided by the sine of theta. So I think you can handle this by putting in your omega that they give you and the r that they give you, and then getting your dividing by g, so you can solve for your h.